Okay, no, thank you. How does it? Sorry.
This is the pointer.
Okay. No, I am. So thank you. I'm Matteo Bianchi from University of Pisa. We talk about human inspiration for the design of robotic system and human-machine interfaces for assistive and medical application. So basically, we live in a world where humans and robots coexist in different environments, especially for what concerns medical robotics. There is a strong integration between the artificial and the human side. So to enable a proper communication and synergy between these two worlds, it is fundamental that humans and robots speak the same language, the same sensory motor language. And especially this language should cover both motion generation in terms of safety, predictability of motion, but also information retrieval, especially with the sense of touch, which is the sense that humans use mostly for interacting and exploring the environment. And we can take human inspiration as a driving factor for developing artificial systems that can fulfill these requirements. So let's start from tactile information retrieval, and let's focus on what is called exteroception. So how to get information about the physical properties of external objects. And in my talk, I will focus more on object compliance, which is extremely important if we want to manipulate delicate objects and interact with deformable objects. And basically, if we want, for example, apply this line of thinking to robotic prosthetic hand that can interact with the external environment, one first consideration we have to take into account is that human fingerpads deform with the environment. So we have soft deformable fingerpad, which can deform with the environment. This can enable multiplication and amplification of grasping capabilities. But at the same time, the deformation of human fingerpad is extremely important to retrieve information from the environment. And we have many sensors and different afferents that are activate. But if we want to translate this deformation onto the robotic side, it is worth mentioning a new class of sensors, which are the so-called soft optical tactile sensor. Basically, these sensors consist of a membrane that can deform, and then they rely on information acquired by a camera embedded in the sensor. And there are different types of sensors which are based on this technology, like digit or other types of sensor. But in this talk, I will focus on this biomimetic sensor, which is the tactile. And this sensor is developed by the University of Bristol, and I will present a work that we have done in collaboration with the group of Professor Nathan Lepre. So the nice thing is that we can exploit vision to retrieve contact information, and in robotics, these types of sensors are mainly used with deep learning methods. And these methods are extremely useful, of course, but they cannot encode the information in the way that the humans actually do. So if I want to get this information from a robotic hand and deliver this information to the prosthesis user, for example, the encoding phase should be similar to the mechanisms that we use to perceive tactile information. This is what we did. Try to use a model-based approach with this sensor. So this is an overview on the working principle of this sensor. There is an outer layer, rubber-like, which mimic the epidermis. And then we have an inner layer made by an elastomer gel. And these two layers interdigit with some ridges that are similar to the what are called papillae in our skin. Basically, they act as a mechanical amplifier in our skin. And in this sensor, by tracking the displacement and the velocity of these ridges using a camera embedded in the sensor, we can infer information about the contact with the external object. We integrated this sensor in our soft robotic hand that we can also use in a version for prosthetic application. But here I want to discuss how to use computational model of human tactile perception with a soft optical biomimetic sensor. So in humans, if we look at compliance perception, there is a paradigm which is well established, the contact area spread rate. So basically, if we interact with a very soft object, the growth of the area under increasing indenting force is larger compared to a harder object, because in the first case, the object warps around the finger pad, so the area growth is faster. So what we try to do is to implement the contact area spread rate with this soft optical tactile biomimetic sensor. And we use information from the camera that was integrated within the object. And basically the idea was to estimate the optic flow, which is basically the apparent motion patterns that we can acquire through vision. And we apply a well-established paradigm vision, which is the time to contact. So basically, the derivative of an area whose contour is related to same isobrightness properties can be retrieved by computing the divergence of the optic flow. And this is used in vision, for example, to infer the time to collision for navigation and so on. If we combine this information with the force measurement that we can acquire by integrating a force sensor with our approach, we can relate the change of the contact area not with respect to time, but respect to force, and estimate the contact area spread rate, which is the derivative of the contact area over the force. And we perform experiments, and we found that with our approach, we can correctly discriminate different specimens with different stiffness. And also, if we have a model of the stiffness properties, of course, we tested with the same type of hyperelastic material, and the model was tailored to these properties, but we can generalize. We can estimate also new specimens with different stiffness to provide a discrimination between different compliance levels. And this is the first model-based approach based on a computational model of human touch used with the soft tactile optical sensor. In the project, we push further this quest for bio-aware design, starting from the observation that humans, during the exploration of objects with different compliance properties, with the soft, so the exploration of soft deformable objects, humans tend to adjust their co-contraction, muscular co-contraction. So what we did was to use a variable stiffness actuator. This is developed by QB Robotics, which is also a SME involving THE, Spoke 9, as my group actually is. And basically this actuator behaves like human muscle, because there are two springs and we can change the position, the resting position, but also the preloading of the spring. So we can control the position, but also vary the stiffness, like the agonistic-antagonistic approach and method that we use with our muscle. And basically what we did was to record the co-contraction muscular patterns during the exploration of different deformable specimens in humans. And we use this EMG to map the control of the variable stiffness actuator. We first verified that different co-contraction profile refer to different specimen exploration. And then we mapped this profile for the control of the variable stiffness actuator. And we found that this control integrated with the method that I previously presented based on a computational model of tactile perception with the soft tactile optical sensor increases dramatically the performance in terms of compliance discrimination. And this is something that can be integrated also in a robotic hand with agonistic-antagonistic behavior endowed with the soft tactile optical sensors and eventually used for prosthetics, for example, but also for rehabilitation and assistive application. The second, so this is the idea, using the computational model of human touch plus embodied intelligence to infer material properties like compliance, and then use this information to provide the feedback, for example, to a prosthesis user. The second part is related to motion predictability. So basically, human-like motion generation in robotics is a well-known topic. There are different approaches based on minimum jerk or other learning methods. But what my group did was to use a different approach. So the idea was we can use functional principal component analysis. Basically is a functional generalization of principal component analysis. We have a basis on functions that can be combined to reconstruct a trajectory or the variation of a function over time. And we applied functional principal component analysis to study human motions for different degrees of freedom. And we found that we can identify a basis of functional components that are ordered according to the associated variance explained. So we can think to have a basis, and we can combine the element of this basis to reconstruct motion. So we can remove an hypothesis for human-like motion generation, and we can combine these functions to reconstruct motion, to plan also motion on the robotic side. So we first start from motion planning at the joint level, in the joint space. And if we want to plan a free motion without any obstacle, we have a closed form solution because we want to minimize a given function, which is this, so the initial position and final position for the joints. And the constraint is that the trajectory is constrained to be the composition of an average posture, an average trajectory, and then the combination of the functional components that we extracted from human upper limb. Okay, in free motion we have a closed form solution using only one functional principal component plus mean function. If we have obstacles, of course, we have to include an additional part in the minimization function, in the cost function, which is a classical potential-based cost function that brings the motion away from the obstacle, still subject to the structure of the motion retrieved from the functional principal components in humans. In this case, the solution is numerical, and we can increment the number of functional principal components to obtain the numerical solution. Everything is very, very nice. We have a very low jerk values, bell-shaped velocity profiles, which are typical of human motion. But we tested this in simulation. We use a kinematic model for our avatar, which is the same with respect to the model that we use for extracting functional principal components from humans. But what if we want to apply this planning to any redundant human-like manipulator, an arbitrary redundant human-like robotic manipulator? There is a mapping that we have to account for. So the first solution that we propose is to work at the joint level, and basically we implemented two Cartesian impedance control. In one case, the first controller minimized the distance between the paradigmatic arm that we use in simulation with the same kinematic with respect to the human arm, and the effector of the robotic manipulator that we want to control. And the second controller is used to handle the redundancy and basically act to reduce the distance between the position of the elbow of the paradigmatic kinematic model we use for planning and the actual kinematic of the robotic manipulator. The two controllers are decoupled because there is a projection in the null space of the secondary controller to make the effect decoupled. And this works in a good way, but of course there is a not negligible computational time to solve the optimization problem in presence of obstacles, and also to provide this kind of mapping. And this can take up to several seconds. And if I want a robotic manipulator that can interact real time with humans, this is not the best solution. So what we do is to plan to apply the same approach to extract a functional principal component, not in the joint space, but in the Cartesian domain, so the end effector of the human arm. We can solve mapping and we can reduce the computational time because we can apply the functional principal component of our end effector, the human end effector, to the end effector of any robotic manipulator, redundant robotic manipulator. Okay, so we found the first 2 minutes, I'm done. So we found that also at the end effector in the Cartesian space, functional principal component can be ordered in a basis, and each element is associated to a given variance explained. And then what we did was to devise the same planning but in the Cartesian space. So you can see here that the structure of the trajectory of the end effector is similar to what we did with the joint space. But of course, in this case, we have also to consider the velocity and the acceleration at the initial time and the end time. And we can find this is a system that can be easily solved for the end effector. If we have obstacle, we can use a set of via points for guiding the trajectory around the obstacle, and we can plan the movement in pieces between the consecutive control point. And also in this case, we can compute the trajectory in closed form. And in this case, it's no more a numerical procedure, and we have a low computational time, and we can optimize for the set of via point that we use. In this case, we obtain very jerk value that are very close to human example, and we prove that we can outperform other state-of-art methods like dynamic motion primitives for planning this human-like trajectory. And these are only some video. We have to perform a more extensive test with robotic manipulators, but in this case, we have two tasks, self-feeding with obstacle and without obstacle. So I'm going to conclude. So we can use a human-centric, bio-aware approach to enhance mutual awareness between humans and robots and the effectiveness of the interaction between humans and robots. And we can start from the implementation of a sensory motor language that can be understood by both the humans and the robots, both in the motion generation and in perception. And the next step could be closing the human-robot exteroceptive loop, relying on computational model of human touch to have information encoded in the same way that humans actually use for encoding and acquiring information about the environment, and integrated the integration of human-like planning with other strategies for collision detection and reaction, like the generalized momentum. So this is the acknowledgement section, all people involved in this work and the funding, and thanks for your time.
Thank you for your presentation. Any questions from the audience? I have a curiosity myself. When you say the computational numerics that you need for these calculations, is this done integrated in the system, or you have a link, external link, and the computation is done by say a workstation connected?
This is a nice question. Yeah, the computation load is very low, so can be integrated and embedded in the system. We have a preliminary version, and we use not a workstation but a simple laptop, so can be integrated, embedded in the system, and can be done in an integrated way with the hardware, because we look for low computational load. This is also a differentiation with respect, for example, deep learning methods that can be integrated but require much effort to be done.
Okay. Thank you so much. Prego.
First of all, thanks for the very interesting presentation. I have a question on the first part of the presentation on tactile sensors. Does it depend how the tactile sensor works and recognize different stiffness on the stiffness itself of the membrane in some way? Is it mimicking the human stiffness of the thumb, or there's an optimization for that?
This is a nice question. So basically, the membrane, the structure of the sensor mimics the structure of human skin. It is similar to human skin, but it's not the same. In our case, this is not important, because we are interested in a differential computation. So if we start from a good recognition of the initial condition of the contact area that we can do by vision, we can apply our approach. Of course, the closer are the mechanical properties of the external membrane to human skin, the better is in terms of biomimicry. But in terms of discrimination of different level of compliance, this is not mandatory, because we are interested in a differential computation which is based on a good estimation of the initial contact area. But this is a very interesting question.